Hi everyone, this is Miss Graham and I'm going to be going through lesson 2-4 with you today. We're going to start looking at equations with no solution or infinitely many solutions. Let's start off with highlighting our learning targets for today. So we're going to identify equations that have no solution, and we're also going to work on identifying equations that have infinitely many solutions. We're going to compare and contrast this to the idea of what it looks like to have one solution as well. Now, we're not going to actually do number one, but we're going to talk about the background of number one. It says, remember that a solution of an equation with one variable is a value of the variable that makes the equation true. So let's look at these three equations we have. We can see there are a couple of terms on the left side, and they equal some terms on the right side. We went through these past couple sections on how we can solve for x and figure out what is that one number that will make both sides of this equation equal each other. We could do the same thing for part B, right? We have two different terms set equal to two different terms, and the same goes for C, right? We have one expression on the left set equal to one expression on the right. We would have to figure out what that solution is. We could go through and solve. We could go through and let's say we're given a couple of different possible numbers. We could plug those numbers into the equations and see which sides equal each other. Then those numbers would be our solution. But looking at this now, is it always the case where we will get x equaling some number, where we will get our variable equaling an exact solution? Well, we're going to learn that no, it's actually not always the case. So if we look to the right column where it says math tip, right, we're just getting reminded that an equation is true when both sides of the equation have the same value. Otherwise, the equation is false. So we're going to possibly see an equation that's false and see what that means. Remember that 2 plus 3 equals 5 is a mathematically true statement because 2 plus 3 has the same value as 5. But what if we end up with something as 2 plus 3 equals 6? Well, we know that's a false mathematical statement, right? Because 2 plus 3 does not have the same value as 6. So again, we're going to see what does this mean in a solving for variables situation. Now, we're going to get to reading the background and the question of number 2, but I want you to start off looking at the bottom right down here with Laura. I want you to start looking at that for a second. So we can see we have an equation. There are variables on both sides, right? So we can see, we're going to start off by solving for x. So they use the distributive property to multiply that negative. Then they start to combine like terms. Looking good. Then they start using that addition property of equality by adding the 9x to each side to start to combine like terms. And then they start moving the 8 to the other side. And you can see, we're now using division property of equality where we divide by 15. And lo and behold, this time, we don't get as pretty of a number as maybe we have before, but that's okay. We can see that our x value, our solution of negative 11/15, is what is going to make this equation true, meaning that both sides of the equation will balance, will equal the same resulting number if I input that negative 11/15 back in for x. So we really here are reviewing what it looks like to have one solution for our equation. But that's not always going to be the case. Let's start reading right above question number 2 and see what else there could possibly be. It says an equation has no solution if there is no value of the variable that will create a true mathematical statement. Interesting. So for this one, what we're going to do is we're going to look at Leo's example below. We're going to skip over Nia's right now, but let's look at Leo's. We can see he starts off having his equation. He uses the distributive property. Perfect. He starts to combine like terms. awesome. That's looking great. He starts moving all his variables over to one side. He starts subtracting the 5x. But wait a minute. Look at this statement here. What happens when he tries to move all the x's to one side to combine like terms? You can see the x's actually get canceled out. Like, let's say we're subtracting 5x from this side. Okay, we do it to the other side. They cancel. Look what's left. We have this statement of 6 equals 17. Well, this is not a true statement. We got to put a slash through that equal sign. Now, in this case, we can't even solve for x at all. It magically disappeared. We now have a false mathematical statement. So what does this mean? This means that we have no solution. So as opposed to Laura's example, she did come up with one solution. Leo solved this mathematical equation and saw there was no solution possible. Now, let's go back up above question number 2 and read through that next sentence. It says an equation has, infinitely many solutions if there are an unlimited number of values of the variable that will create a true mathematical statement. Well, this is so interesting. Wow. Okay. Well, let's look at what Nia has to say. Let's look at her work when she had her equation and see what she did. So she started off just like the other two students by using that distributive property. And then she saw, okay, I have to combine like terms. And then she started moving her variables over to one side. And you know what? I can see that she has something similar happening to her like Leo had. When she moves her variables to one side, you can see that both of them actually cancel out, meaning that our variable disappears again. This is so interesting. Oh my gosh. Okay, so looking at our statement, what we're left with, we see we have 2 equals 2. Well, yes, from a mathematical perspective, we can say, yes, the number 2 does equal the number 2. That is a true statement. But what happened to our variable? What does this mean? This means that our equation has infinitely many solutions. So let's write that down. Infinitely many solutions. Wow. Okay, so infinitely many solutions means I can put any number in for x, any number at all, and both sides of my equation will balance. They will both equal out true. Now, looking at the above question number 2, it says, okay, we have these 3 students. They solved the following 3 equations shown. We have to identify each of the equations as having one solution, no solution, or infinitely many solutions. We identified everyone else's, but Laura's, we saw the one solution, what it was, but we also have to write down that it is only one solution. Let's go ahead and turn to our next page, page 26. In the margin on the left side, we're going to practice determining solutions of given equations. So we're going to look at number 3, 4, and 5. I will tell you from these 3 equations, we have 3 different types of solutions. We are going to get one of each as we are solving through them. So I'm going to practice all 3 of these with you, and then I'm going to give you an opportunity to practice some on your own. Let's start looking at number 3. So I'm going to go ahead and I'm going to write it down in my margin. So it's 3 times 2z, and I like to use my z's with a slash through it, just so you can keep that for future reference, plus 4. It's going to equal 6 times 5z plus 2. So reviewing kind of what we know already from the past couple of sections, we're going to be using the distributive property actually on both sides. So for me, I'm okay with doing the distributive property for my next step on both sides. So when I do this, I get 6z plus 12 equals 30z plus 6z. Oops, sorry, hold on. Let me try that again. That is a 2. That's why I always have to clarify that my z's have a line through them. It should be 6 times 2. That will give me 12. Okay, the next step is for us to get all the variables together, so all my z's. I have a preference of getting them all on the left side. So for me, I'm going to subtract 30z from the right side. It's going to be on the left side. So now when I do negative 30z and a 6z, I'm going to get a negative 24z plus 12 equals 12. My next step is going to be to combine all the numbers together. So I'm going to subtract the 12 from each side. And then I'm going to be left with 24z. That's going to cancel out. And this one's actually pretty cool. Think about it. It's 12 minus 12. That gives us 0. Well, don't freak out yet. These are actually some of the nicer types of problems. It's not going to be a no solution or infinitely many solutions because we still have a z as our variable. The last step of what we're going to do is we're going to divide by negative 24. And we end up getting z as 0, right? So this means we have one solution. And we found out what the one solution was. It was z equals 0. Now, let's say you're not necessarily sure about this. Remember what we can always do. We could always check our solution. Think about what check means again. Check means that we can put z as 0 back into the original equation for z and look to see if both sides balance out. Your teacher might give you the option of you don't have to do this every time, or you might have to do this every time, so make sure you're listening to their suggestions. All right, so for us, we're going to try it on out. We're going to put 0 back in for z, so I have 3 times 2 times 0 plus 4. And we're going to see if that equals 6 times 5 times 0 plus 2. Well, following a kind of our order of operations, I'm going to work inside our parentheses and work outward. So I'm going to multiply 2 times 0. That gives me 0. Then I'm going to add 0 plus 4 and then end up timesing that by 3. Over here I have 5 times 0. That's 0. 0 plus 2. And then I'm going to times that by 6. So right now we have 3 times 4. And we're going to see if it equals 6 times 2. Well, lo and behold, it does equal. We have 12 equals 12. Cha-ching! That means we did find the right solution. It is balanced. Now let's go ahead and look at number 4. I'm going to do it in the margin to the right for me because I have a little bit of space, but you might also have some space in your margin in your left still. So let's start off by writing the equation. 3 times x plus 1 plus 1 plus 2x. Ooh, this is a fun one. Equals 2 times 2x plus 2. Ooh, and I ran out of a little bit of space. Plus x. So for me, again, I'm going to work on the distributive property first. And I feel okay with doing both distributive properties on each side. If you want to break it up into simpler steps, you're more than welcome to. But I'm going to go ahead and combine them into one. So I end up having 3x plus 3 plus 1 plus 2x equals 4x plus 4 plus x. My next step is to combine like terms. So I see I have a 3x and a 2x on my left side, so I know that's a 5x. I also can see I have 3 and 1, so I'm going to add those together and get 4. On my right side, I have a 4x and a 1x. Remember, there's a 1 in front of that. So that gives me 5x, and then I have a plus 4. Now, we could actually stop at this point if we wanted to, because if we are looking at this equation, we can see we have the exact same thing on one side and the exact same thing on the other. If this is the case, what's going to happen is we're going to have infinitely many solutions. But to continue to show you what it looked like exactly with the problem before, I'm going to go ahead and continue my work to show you that it will be infinitely many solutions. So let's say I want to get all my variables to one side. So I'm going to move it from the right side to the left side by subtracting the 5x. What happens is the variable cancels on both sides. And now we're left with 4 equals 4. This is similar to what we did on the previous page, on page 25, right? Where we had the same number equal on both sides. So this means that we are going to have infinitely many solutions. This means that any number that we plug into this equation will yield the exact same number on the other side. So that's pretty cool. All right, well, by process of elimination, we kind of understand which example we're going to have for number 5, but let's just practice this together. We're going to go ahead and write number 5 down. Should be 8b plus 3 minus 10b equals 2 times b minus 2 plus 3. This time we only have to use the distributive property on one side. So that's nice. So I kind of am going to start to combine some of the steps together. Again, if you feel more comfortable doing it a little bit slower, one step by one step, but kind of for time's sake of the video, I want to make sure that you see how we're able to bring everything together. So on my right side, I'm actually going to combine my terms. So I'm going to get negative 2b plus 3. I'll use the distributive property, so it equals 2b minus 4 plus 3. I'm going to combine like terms on the right side as well, so I'm left with 2b minus 1. And then the left side has negative 2b plus 3. All right, as we continue through this problem, let's see what's going to happen. Oop, and some of you probably are realizing, wait a minute, Miss Graham. Did you notice that there's a negative in front of the 2 right there? I actually just noticed that right now. So like I said, math teachers make mistakes all the time. I just realized that mid-problem. So I want to make sure I go back and add in that negative sign. So really on the right side, we have a negative 2b, and this should be a plus 4. So I might have to erase what I got down here, which is totally okay. So let's see what we have now. I should have a negative, let's try that again, not with the highlighter. So I should have a negative 2b plus 7. That's looking a lot better for me. All right, so looking at this, okay, let's see if we can move all the b's, all the variables to one side. My preference is to the left. We can see they end up canceling out, so we get the statement 3 equals 7. Wait a minute, looking at this, that is not a true statement, right? So we put the slash through that equal sign. So this means there are no solutions possible. So we write no solution. There is no number that we can put in for our variable b, which will have both sides of our equation equal each other. So right underneath number 5, we have another little paragraph that kind of just reminds us of, okay, what other values can we get besides having one solution? So let's read it. It says some equations are true for all values of the variable, just like what we found. This type of equation has all real numbers as solutions. Maybe you remember last year learning about different types of real numbers. We're going to get to that later on in the year and what that actually means. Remember, this equation has infinitely many solutions. Other equations are false for all values of the variable, and as a reminder, this type of equation is no solution. Let's start looking at number 6. I'm actually going to read through it and then have you work on it on your own for a little bit. So let's look at number 6. It says, which of the following equations has no solutions and which has all real numbers as solutions? It says, explain your reasoning. So go ahead, look at A and B, look at the work that I have on the right side for number 4 and 5, and see if you can make a prediction looking at these equations and seeing, okay, which one is going to be infinitely many solutions, which one is no solution. Go ahead and pause the video right here so you can explain your reasoning. All right, let's start looking at number 6a. Here we can see we have 3x plus 5 equals 3x. Maybe some of you started looking at this and started thinking, wait, a number cannot be equal to itself plus 5, right? So 3x plus 5, that wouldn't make sense. This extra 5 there will not make any sense in this problem at all. Why is it even added onto there? 3x should equal 3x, not 3x plus 5 equals 3x. From this idea, or maybe some of you actually showed some work. Maybe you said, hey, I'm going to get all the variables to one side. I'm going to actually move them to the right side because I have my number on the left. And maybe you got a statement like this. We know it's going to be no solution. A number, right, cannot be equal to 3 times itself plus 5. So for me, I'm going to say it's no solution since 3x cannot be equal to itself plus 5. Again, by process of elimination, we know what part B is going to be. However, let's start looking at it and breaking it up. We can see we have 4r minus 2 equals, 4r minus 2, we have the same thing on both sides of our equation. Interesting. We know it's going to be all real numbers or infinitely many solutions since the expression is equal to itself. If you wanted to go ahead and continue to show, okay, how I can solve, right, you could definitely do that. But you could also look at it from an analytical sense, right? So we could look at it from that way. So for me, I'm going to write it down as we're going to have infinitely many solutions since the expression is equal to itself. Now, maybe some of you are thinking, what is an expression? What does that really actually mean? Well, an expression is part of an equation. An equation has the equal sign, but an expression is basically half of it. So 4r minus 2, that's an expression. It's when you have multiple terms together. It's part of the equation. So we can see we have one expression equaling another. So that gives us infinitely many solutions. We're going to go ahead and look at number 7 right now. It says a student claims that the equation 2x plus 6 equals 4x plus 4 has no solutions because when you substitute 0 for x, the left side has a value of 6 and the right side has a value of 4. Is the student's reasoning correct? Explain. So I'm going to have you pause the video right now. I'm going to give you an opportunity to read through this problem and to go ahead and try answering it. All right, are we ready? Okay. Number 7 says, yes, let's substitute x as 0. But wait a minute, where did this value come from? Where did x is equal to 0 come from? Was it just a mathematical guess? Well, just keep in mind, just because we pick x equals 0 doesn't mean it's going to be a solution. It doesn't necessarily also mean that it's going to be an equation with no solution. What we could do is we could solve this equation and see what we get for x, right? Instead of randomly guessing. Okay, let's go ahead. We're going to do this. We're going to solve for x, looking at the equation. So we have 2x plus 6 equals 4x plus 4. Let's say I subtract 4x. And just because of space purposes, I'm going to do a couple steps in one. I recommend that you find more space so that way you can work with it. But what I end up getting is negative 2x equals negative 2. And then what happens is I divide by a negative 2 underneath my x and do the same thing to the right side. So I get x equals 1. So looking at this, just because we picked x equals 0 doesn't mean it's a solution, and it doesn't mean that the equation doesn't have any solutions. When we solved it, it gave us x equals 1, so the equation has a solution. So I'm going to go ahead and I am going to write that down here because we're actually going to skip over 8, 9, and 10. So we got a little bit of space below. So we're going to say, no, just because x equals 0 is not a solution doesn't mean the equation has no solution. Solving gives us x equals 1. So the equation has one solution. And I apologize if my handwriting's a little chicken scratchy. All right, so now is the time where your teacher is going to assign you some homework. So go ahead, make sure you check Schoology or you check your calendar to see what your teacher designates as your homework for tonight. For Miss Graham's class, our homework tonight is going to be page 27. So we have page 27, and it's going to be numbers 15 through 17 right here. It says to solve each equation. If an equation has no solutions or if an equation has infinitely many solutions, it says explain how you know. What I'm going to say is you don't have to explain. I'm going to say show. That means you could show work. Show how you know. All right. If you do end up getting a one solution equation, then I would suggest that you check your answer just in case. I'm not going to, say you have to, but I am going to highly suggest that. All right, go ahead and get started working.